this could be a solution, but then you are calculating a metric that becomes comparable, but that it's wrong. Like mainly you are underestimating a lot the distance and speed covered. So depending on what you're trying to tell to the audience, you could say, this is comparable. And so on average, this species moves faster than this species, but actually both of these metrics are wrong. And probably all of them are calculating a speed that is lower than what it actually is. And Chris will show, I don't remember when, in a couple of days, maybe some other methods that are more accurate if you're really interested in speed. So this way of calculating speed is very, very sensitive to sampling frequency. But there are methods that are less sensitive to this.
Mm-hmm. Because there are papers that they have just split the animals, maybe mainly the paper from Tucker from 2018, because they have many mammal species with different sampling rates. So they just split groups of animals depending on the sampling, but they do not do this thinning or nothing related to this. So
they split the animals in...
Yeah, because this is what I have done with the jaguars with my own data, because we have many different sampling frequencies. So, and I cannot, lower the resolution of these jaguars that they are at 30 minutes because I'm losing very precious information there. So do you think that is the best solution is this, or just splitting these whole data sets in small chunks of animals that they share the same sampling frequency?
Oh yeah, if you have that, yeah, of course. If they cross for some time, then I would say you just take a chunk of your data for all of them, a chunk in which the sampling frequencies match, and then you can use that. Of course, this assumes that that little chunk of data that you're using is representative of the entire movement of the animal. This you don't know, right?
Yeah.
Because if the animal is migrating and then you're just sampling the local movement, you have no information about their speed of migration, for instance.
Yeah, that's mainly with resident individuals, yeah.
I think all of these are very valuable options. You just have to be aware of what the consequences of whatever you do. So like the reason why we go through all of this is just to make you all aware of having this second thought in the back of your head. Okay, if I do this, what's going to happen to what I'm measuring? But then if you declare it and you do it with purpose, then it's all fine.
Yeah, because
and it's very valuable to say, I don't want to throw away all this data, of course.
Yes, mainly because we were people working with mammals that normally has not too much data as we have with the vultures and all these things. So losing data is not an option sometimes.
Yeah, definitely. Yes, just to conclude, a couple more things about the thinning, but we already talked about this. I was saying we underestimate the distance covered and the speed unless the animal is going straight. So if the animal is going straight anyways, like in migration, then probably your underestimation is not big because the animal is anyway going straight. But the more tortuous is the track, the higher risk you have of underestimating speed and distances. Yes, so always report the ground speed together with the rate at which you sampled. Be aware that there is an effect of sampling rate. And then just something I mentioned earlier, be sure you look at the operational sampling rate. Like don't trust blindly the scheduling that you gave to the device because sometimes it doesn't really match what you get. And yes, and now we can go to our script. Oh, which meanwhile changed its name. It's not script number 2, but it's script 5B.
Sorry, you mentioned that you just uploaded a newer version?
Yes.
Okay, so
maybe we can close all of these. Yeah, should be this one. So I'm gonna set my working directory to the data folder. Have you worked with data already? I haven't followed, I don't know, but you should have a data folder with some files in it. And so,
it's my computer here.
yeah, good point. I was like, what is this project that it's open here that I don't recognize?
Open the visualization script and there you just copy my.
Yes. Did you all find the script? Okay, so now we are gonna just explore a little bit some different data sets. We will look into these functions. These are functions from the move-to package again, and they just help us to calculate very easily the metrics we talked about. And as Anne mentioned earlier, there will be a little bit of jumping between different data sets that suit our examples best. So we're gonna work with bats, we're gonna work with buffaloes, with Leo the vulture, and with fishers. Anyone could not access the data folder, or? Did you find it? Should I continue, or maybe I wait for a second? Yeah? Okay. Okay, so we first look at bats, and we're gonna talk a little bit about the temporal organization of the trajectory. So mainly number of locations in a certain time window, and time lag, and how to extract this information. So the easiest way to get the total number of locations is just n-row. So the move to object, as Anne mentioned earlier, it's in the end also a data frame, so we can just get the total number of locations by using n-row, because each entry is one event, so each entry is one location. With the function empty and tracks, we also get how many different trajectories the move to object recognize different animals. Each animal has a trajectory, and so we can get here that we have 17 bats or 17 trajectories. And then if we look at the table of that, we also get how many locations we have for each bat. Here it's a bit confusing because the bat's ID are also numbers, but if you look at the number below, these are the number of locations for each ID. Time lag is calculated simply as using this function, empty time lags. By default, it uses the unit that the function thinks is more appropriate, depending on what is the average time lag. So in this case, it chooses to use seconds, but we can easily change that in two ways. Either we reset the unit, so we change the unit of time lags using the set unit function, or if from the beginning we know.
So there's, yeah.
What?
This is an old, yeah. So actually now the empty time lags code has the option units. So we added this.
It's here. Just.
Ah, sorry. Okay. I was like, oh no, it's the old code.
No panic,
sorry,
no panic. But it's an option. You know, if you calculated it earlier and then you want to switch it, you can still switch between units. Sometimes it's handy, but if you know from the beginning you want it in hours, you can just do here, add these argument units and calculate it in the unit you want. And the same for all the other metrics that we're gonna look at. And so now the time lag is in hours. And as I mentioned earlier, time lag, but also distance, speed, direction are properties of a segment. So if we look, we said we have 17 tracks, and if we look at the number of NAs in the new variable that we calculated, we have 17 NAs. And this is because the So if we look at the tail of, in this case, the last trajectory, we see that the last value is always empty value. So one of the first things you do, because you don't trust your devices or because someone sent you the data and you have no idea how often data were collected, is that you look at the distribution of time lags. So here we can see that most of the data are collected in less than 1 hour, I would say. But then there is some locations here at a time lag of 20 hours and 45 hours. So right now, this is just to have an overview. I don't even know why this data were collected like this. But of course, you can always look at shorter time lags. And in this case, we are curious about time lags that were collected less than 1 hour, sampling frequency. And then we look, okay, most data are actually every 10 minutes, I think. This is 0.15 hours. Yeah.
Just to make sure
Thank you.
Just to make sure if I'm understanding, the time lag basically is when you don't have the data, like is this gap of the data? No, it's a different.
Yes,
or is
it's the gap
basically-
between locations.
Okay.
So I think now you have some devices that collect every second, sometimes even multiple points a second, but usually you never have a continuous tracking, right? So it's always this gap, whatever it is. It could be a gap of 1 second, it could be a gap of days if you lost your animals, and then especially if you go radio tracking, which might be the case of these bats, because these are radio tracking data, it might be that those 20 hours gap or 50 hours gap is because for 1 day was bad weather, they didn't go out to pick the point, and then you have a big gap.
Thank you.
And this is exactly where you can see these like natural chunks of data, right? You can say, okay, most of my analysis I will do on my 10-minute sampling, but if I want to do, I don't know, something about space use over months, then maybe I don't care that there is such a big gap, and I can still include all the data I have because this gives me a longer span of time. So it always depends. Am I interested in high resolution behavior, fine scale, or am I interested in long time series of data? And depending on that, you can decide what to include.
So in I think this is the line 60, it says that by default, it's the most convenient unit. So if you're setting that time length for an hour, but how does it choose the most convenient?
No, that it does it by default. So if I don't specify any unit, probably in this case, since most of the data are collected I don't know why, it could have picked minutes actually. I don't know if.
I guess because there are some locations that are seconds apart, so it takes, I think.
Maybe the minimum difference, and then it takes that as a unit.
This function is from another package, so it's not.
Is diff time or? Yeah, but yeah, basically it means depending on what the distribution looks like, it takes a unit that seems convenient, but then you can change it depending on what you're interested in. More questions? No. Okay. Distribution of time lags. Yes, number of locations in time. Of course, we might be curious to know how many locations were collected in a given time window, in a day, in a month, and so on. So this is just to show you an example of how you can do it easily. With empty time, you saw with Anne, you can extract a vector of all the timestamps of your move to object. And then, so this is just the head. We see the sequence of timestamps. If we want to interpret the data, this is a way to convert to a local time zone because data are collected in UTC. And we know these paths were data that were collected here, around here. So in my computer, and I repeat this again, that's something I mentioned earlier in the presentation, with also names, you can get the names of the time zones that are recognized in your individual computers, which might be different. In my computer, this time zone here, it's called Europe, Zurich. And so now I can see that in Central European summertime, we see a slightly different time. That might be useful if you, here it doesn't really matter, it's just 1 hour, 2 hours apart, but especially if you're looking at very different longitudes and you're interested in the behavior of the animal, whether it's nocturnal or diurnal, it makes a lot of sense to look at local timestamp.
And that takes in consideration the daylight cycle.
Yes, so here it's summertime.
Yeah, okay, perfect.
Yeah.
Takes in consideration the
Yeah, here it's summertime
daylight
because it was in June. So in June, it knows that there is this daylight saving. But again, it's like Kami mentioned earlier, I think it's just for your behavioral interpretation of what the animal is doing relative to sunlight, because otherwise for all the calculation, especially time lag and so on, I would always refer to the UTC, because then you're sure it's standardized. So here we can use the group by function and the lubridate package as very useful functions to work with time objects. For instance, with the function hour, you just get the hour of the day. With the function day, months, and so on, you can just get little parts of your timestamp. So here we group by hour, and we just calculate with n the number of location. So by default, this is a SF property. By default, whenever you do this calculation, the geometry gets inherited. So you can just drop it. So the geometry means here in this multi-point object, in this multi-point column, you will have in each entry all the points that belong to that group, so to that hour. So depending on what you need, but usually you don't need that information. And then you can just drop it here with this ST drop geometry. Here we just do the same, but we give it nicer name. We group by months, hour, and then we drop the geometry. And so here we have the same information, just a bit more organized. Then, spatial organization. So we are gonna now look at distance, speed, and also relationship between speed and turning angle. Speed and time lag, which is what we talked about just before the script. So to calculate distance is very easy. We can use the function empty distance. Again, we can set the unit in which we want to get the distance, in this case meters. Again, you see there is 17 NAs because there is always a NA at the end of every trajectory. And then, as I also said in the presentation, this is kind of a typical distribution that we expect from speed, from distances, and also from speed. So usually there is low distance and low speed that an animal moves, and then occasionally they move faster or longer distances. And for the speed is also very similar. There is empty speed as a function. We can set here the unit as meter per second. And then also we look at the speed. So speed is very sensitive to gaps and also to outliers. So we will see at the end of the script how speed is also very good to discriminate and filter out outliers. And so here we see, for instance, there are these very, very high speeds that are obviously unrealistic. I think a bat is not gonna fly more than 20 meters per second. And so we can just look at realistic speeds. And again, we see that this is the usual distribution that we would expect from speeds. And something interesting that follows up on what I said earlier, it's the relationship between speed and time lag. So now we're gonna make a data frame that has the time lag and speed that we calculated earlier for bats. And we're gonna plot them one in relation to the other. So we see here that for short time lags, we have a very wide distribution of speeds. So for short time lags, animals are going fast, are going slow, but then the longer the time lag, the slower the speed that we collect. And this is again because of what I said earlier. So a lot of the distance that they cover, like all this path, is ignored because we don't know what happens in between location. So here there is a 3-hour time lag, and probably in those 3 hours the bat moved a lot, but we couldn't see it in our data, and so it looks like it moved very little, especially because we know these bats are foraging, so they move like this. In 3 hours, they are probably end up in a very small location that is very closer to the previous one, and so it looks like they moved very little, but actually they did a lot in that 3 hours. And so basically, high speeds and realistic speeds are only possible when the time lag is short enough for that species. Then again, it depends what species we are looking at. This is with bats. Probably if we look at buffaloes or larger animals, the effect is not so strong as we see here. And here is also an example for a nice plot. I'm just gonna run all of this together. We're gonna plot the trajectory covered by the bat, and we are coloring segments by speed. And this is just to tell you what the animal is doing. So these bats are going, they forage with this very high turning angle. They move around a lot when they forage. And so it's pretty clear why, if we have a very long time lag, we might not record the realistic speed. All good so far? Questions? Good. Now we look at direction of movement, azimuth, and heading of movement is what I said, like just to highlight the difference. Here we're not gonna look at heading because we don't have this information in the tag, but again, the difference between heading, that is the body posture, and direction of movement, that is what we are gonna actually calculate. This is just what I repeated. You also have in the script. To calculate direction, again, it's very easy. There is this function called empty azimuth, and direction is calculated in radians between minus p and p. And if we look at the histogram, this is the direction of movement for bats. What are these bats doing? Do you have any idea? Why is the direction of movement looking like this? Exactly. So now that we plotted it already, this is very easy to interpret. We know what they're doing. They're just foraging, changing their angle of movement all the time. So it's pretty obvious that this is what we are gonna get. If we had a migrating animal, this would look very different. But we plotted the data, so we know it fits, yes.
So would that also apply for like resting, thinking that the device would like capture with some error the same place and the angle might be all around?
Yeah, very good point. So if you have an animal that is stationary, so most of this analysis I would say that you would first select or filter a moving animal. So you could already put a filter on speed before doing any other analysis, because this could happen. If you have a stationary location, then the error of the GPS gets big, and then you would see a lot of movement in all direction also for GPS error. Yes. So, turning angles. As a repetition, the turning angle is the angle of one segment relative to the previous one. So it's a measure of persistence in movement direction. And in this case, we're gonna just pick one bat as example, bat number 191. And as I mentioned earlier, the turning angle is a property of two segments. So at the very beginning and at the very end, you will have an NA. So you will have always two observations less than the number of observations in a track. Also, the turning angle is in radians between minus p and p. And minus negative values would be turn to the left, positive values, a turn to the right, around zero, same direction. And so here we see that there is some persistence in direction for the bats. And again, just because we know this data set, we know these bats are moving along linear structures. But here, for this reason, we added also another example from a different animals for buffaloes, just to show you how it would look like. I mean, I showed it in the presentation already, but this would be kind of a more regular distribution that you would expect from turning angles. Questions?
Can I ask a question out of curiosity? Did anybody get a distribution from 0 to 6? Or you all got negative pi to positive pi? Sometimes. Okay, thank you.
Yeah, something we discovered from the baggage. Elam, instead of getting minus p to p, she was getting 0 to 2p. 2 pi, sorry, p. So from 0 to 6, from 0 to 6 instead of minus 3 to 3.
In the last workshop, there was one other person, but
We still don't know why this is, but usually you should get minus 3 to 3. Yes, so now we are just going to look at a case study in which you want to analyze the relationship between azimuth, turning angle, and speed. And for this example, we're going to use Leo. It's a turkey vulture. And just to get familiar with the data, we will plot the trajectory of Leo. It was tracked for several years. And we see here it's migrating back and forth to its nest. Actually, we know from this animal that was sitting more or less on the same nest for several years. And then to get familiar with also the time gaps and irregularities, we're going to look at the distribution of location per year and months. And so we can see here in this table that there is at some point a big gap in 2012. And so just for convenience of this analysis, we're just going to take all data that are precedent to 2012. And now we are going to add to the data set the azimuth, so the direction of movement, the speed, and the turning angle for each of the segments. And then here we're going to do, let me see if I can show this better. We're going to do something that we don't recommend doing, but that for the purpose of this, I think it's nice. So based on what we know of this species, we're just going to arbitrarily categorize its wintering, north migration, breeding, and south migration times or seasons. So usually you would do this with, we will show you actually tomorrow how you would do this in a better way. But just for the purpose of this example, we are going to decide that Leo is wintering from January to March. Then in these 2 months, April and May, it's going to go on a north migration. Then it breeds from June to August, and then south migration. And also we're going to save this data set because we're going to use it tomorrow again. Then after we did this nice exercise, we are also, as I was mentioning earlier in a reply, we are going to look at when Leo is actually moving. So we're not interested in all the rest. We're going to put, I guess, more or less of an arbitrary filter, but saying whenever it's moving at a speed that is higher than 2 meters per second, it's actually moving. And so now, finally, we can look at the relationship of speed with direction of movement for only those segments in which Leo is moving. So we see here, maybe I make this larger again. We can see here that there are certain directions in which the speed is always higher. And so, of course, we saw that that's why it's so important plotting the data. We saw already that this animal is migrating twice a year. So we can imagine that around 180 and 0, these are the direction of preferential migration. And so we expect the animal to travel faster in those directions. But then here, to have it even clearer, we are going to do the same plot, but we're going to plot it separately for every season. So we can see here that north migration is about 0, more or less. It's going, not, as you saw in the plot, it's not really going north, but it's going northwest. During north migration, south migration is southeast, sorry. And then here in the wintering, we will see later that maybe we did a little mistake in classifying because we would expect it, like in breeding, to be more or less moving in all directions at the lower speeds. But here we see that there is a little bit of difference. So we can see this more clearly in the next plot, which is going to show the same information, but in a fancier looking plot. So this is a type of plot that is called windrows. Usually it's used for winds. But here we're going to use it on the behavior of the animal. And again, we are going to have different panels for different seasons. And here we see again that the highest speed are reached in those preferential migratory directions, so north migration, south migration. And then in the breeding, it does what we expect. Pretty much it's going to sit on the nest and look around for food. And then during wintering, we realized that we might have made a mistake when we classified, because we decide based on our arbitrary decision that in those months was wintering, but actually we might have included a little bit of both south and north migration during the wintering, because we see that it goes both directions. So to show again was there a question? No. Sorry, no. Just to show again the difference between looking at azimuth and looking at turning angle. Here we're going to do a similar exercise with turning angle. Again, simple scatter plot. We see here we don't see that difference anymore that we saw earlier. So earlier we had a difference in north migration and south migration in the direction, and here is the same, because this is an angle relative to my previous segment. So both during north migration and south migration, Leo is moving straight, and so pretty much maintaining the direction, its direction of movement relative to the previous step. And again, during wintering, we see a little bit of error here and there. Still there is some directionality that we would not expect in wintering. And then same exercise again, using the windrows, exactly the same. So here we see both north and south migration, there is some directionality. Highest speed are only reached when there is the most persistent movement. And so this is again kind of a property of movement. If the animal is going very fast, it's harder to turn. Before turning, it has to slow down. Just not physically possible to go very, very fast and turn also very fast. Okay, any questions so far? Please.
Is it possible to add the average of the per-bean azimuth in these plots, in this GG plot? It's just because I've mainly used circular, I was not able to, the circular package, I was not being able to do this with GG plot. So, or
to add the average in like a line, or?
Yeah, of the direction of the animals, of the vector.
Probably yes. I mean, right now I wouldn't know on the top of my head, but I think instead of geom histogram, you would add like a geom line. Then you would first calculate externally what is the average rate direction in radians, and then you would add it to the plot as a line or as an arrow or something. I've never done it, but I would think it's possible for sure. Yeah.
So the empty turn angle package gives
Sorry,
out
again? A bit
the
louder?
empty turn angle that
Empty turn angle?
yeah, it gives angles in radians.
Yes.
Yeah, so while plotting we are getting it in degrees. Where did you like kind
Oh,
of?
we changed it at some point here. No, here chord polar start P, and then no, we just changed the labels, yeah. Just here in the plot, we said that the labels in this order are 180, 300, just for interpretation, it's easier. But you could also have it in radians.
Okay, but the values still remain in radians.
Yeah.
Okay.
Yeah.
Is there a way to like kind of convert the actual values to like within the package?
To convert it?
To degrees.
I mean, also here with this, you could change it, I guess, just setting the units. The units package is pretty flexible, so I guess you could have that in degrees if you add deg. And here we are leaving it in radians, and we are saying that the start, it's at P, which is the top, and then it goes clockwise. Yes. Yeah, and here also the limits.
Sorry, just to understand if I understood correctly, the 360 is just a label that should be minus 90.
Mm-hmm.
Okay.
No. It should be minus p to p, and instead we are converting it for easier interpretation 0 to 360. But it's just the labels.
Yeah, but the 360 and 0, are they not overlapping?
Yeah.
Is 270 or
Ooh.
it's just the label, I think, in the plot that. Yeah, in the script on
No,
the
but
left.
I think it's because
yeah.
it's just the label. This is wrong.
Yeah, no, exactly. I think it's
Yeah,
only the
this
label.
is the 0, 90, 100. What is it? 270. Yeah. Good point. Fixed. Thank you. Is it also in the previous one? Oh no, in the other one? Ah no, in the other one we use south, west, north, and east. Yeah, because it was geographical. Yeah. Good point. Thank you. No more question about azimuth, because now we change topic and we go to outliers removal. No? Good. Okay, so now to make an example about outliers, we are going to use again the bats and the buffaloes. So Anne mentioned something earlier about this MoveBank visible, and this is because in MoveBank, if you upload your own data set and you realize there are some outliers, you can mark them from the beginning. So this prevents people from other people or yourself from downloading those outliers, because by default, when you use the MoveBank download study function, the remove MoveBank outliers is usually set to true by default. Should this not be the case? Oh, right. What is your password? Anyways, this is just for a short example. But you can just use this empty movement visible to basically get out what are those points that were already marked as outliers by whoever uploaded the data set, basically. And then you can use this empty filter movement visible. Maybe Anne showed this earlier, I'm not sure, but it's straightforward. And then what we're gonna do next is just...
No, yeah, so I mentioned before that, like, for example, if you have marked the outliers in MoveBank, but you want to recheck what was marked because maybe you didn't mark it and somebody else marked it, you can use the option remove, what is it?
Remove
MoveBank outliers and set it to false, and then you download all data and can revisit how the outliers were removed. But maybe you downloaded it and then you actually agree with the removed visible ones, or you want to compare the two, how you removed them and what was removed in MoveBank. So then you can just use the empty filter MoveBank visible function and remove it again, and just remove those that were marked as visible false. It's just it's probably you're not going to use it often, but it's just there if you would like to use it.
Yeah, unfortunately, what happens in most cases is that you don't know yet what are your outliers, so you have to find out. So a good way is plotting your data, if you're lucky. So here we have the buffaloes data set, and you already saw this morning when Kami had this presentation up and he was looking at the buffalo data set, and there was this big jump going there. So this is, we use data set that have problems on purpose. So here we're gonna see this again. If we map our buffaloes, you see that here there is this point over here. So in this case, it's very easy because this point is out of all the other points. So it's pretty easy to get what are these coordinates. So you can use the SD coordinates, and you have here all the all the longitude values, and we use which max to get what is the value that has the maximum longitude, and we can just drop it. So we drop it, and then if we plot the data again, it's gone. So this was the easiest case because it's very isolated compared to the rest of the data points. Yeah, exactly. I just remembered this. So Anne asked me to mention that some of you might have devices that have empty locations as 0, 0, because we are gonna look later at how you can, if you want, you can interpolate locations and whatever, and this assumes that the locations are empty. But sometimes some devices, for some reason, they think that 0 is empty, and so they will put locations that were not collected because of missing satellite connection, 0, 0. But 0, 0 is a location on Earth, because especially if you use spherical coordinates, you know 0, 0 is in the middle. And so you have to be very careful and look at what your devices do, because if you have 0, 0, if you work in that area and you have 0, 0 as your missing coordinates, you might get into headache of trying to figure out what are outliers and whatnot. Any point showing up?
The problem is the points are not showing up for the viewer.
For the map view. But the background, yes? Also no.
Appeared and then disappeared.
In line 5 or something of the script, did you actually load this track?
I just reloaded the track and I still got the map with no points on it. In his map view.
But then they would get an error that the object doesn't exist. They wouldn't just get no showing up of the points. Error.
Maybe here is in Buffalo and on TV.
The map view package, do you have loaded? Yeah, no, I know the map view, yes, you have. Okay.
It doesn't work?
No. To zoom out, zoom in.
All right, I think some other.
It's interesting because here she has buff geometry.
Yeah, and if I click on it, I zoom in, I just don't see anything.
Nobody can see the points.
Some people see the background, some people don't.
I'll recheck in a second if I moved the wrong file. So if you actually have an empty.
No, it has. Like if you examine the geometry, it's got points in the geometry.
Well, from all things that went wrong today,
I mean,
it's not
but
that important.
but did you follow the visualizations script before and it was working?
It's loading the points. It's loading the points, so it's reading the points.
Well, it was just one example. We'll make sure we solve this because it's very useful to use map view, but for this example, it was just a quick, Who knows? 2.11.2, but it should be the same for all of you because you should have loaded it when installing the AniMove package. So. But anyways, it's.
So many of you have now. So all this was because like 3 days ago, R updated their version to 4.4.1, and now you all have that. And maybe that's the issue. Because everything, so I have 4.40.
Yeah.
And the other one is so new that there could be a bug in there. Just wait 2 days. Bugs can be really particular. So maybe the day after tomorrow it works. So that is just an idea because it's really, if anybody has version 4.4.0 and it doesn't work, then it's, yeah? Okay, damn it. Okay. too easy of an explanation. I don't know.
But it doesn't affect the rest of the lecture, so it's fine. This is the good point. We'll make sure we figure it out in the next days. But anyways, unfortunately, this is like the yeah. We'll find. I mean, maybe later or tomorrow we just borrow one of your computer and we try to figure it out. But I mean, for the moment, it doesn't matter. Anyway, this is like the most beautiful example that you probably will never have. So most commonly, what you end up doing after inspecting your trajectory and so on, a lot of these outliers get removed with speed. So that's what I was mentioning earlier. If you have this animal that is mostly stationary and then you have these starts of like GPS error jumping around, then you will see that basically a big distance has been covered in very, very short time, and then you have these very big these very large speed values. So often it's used speed as a metric to remove, to filter outliers. So here we make again an example with the buffaloes to remove that same point. Do we have to? Yeah. So we first arrange by ID and by timestamp. And then here, probably Anne showed this example earlier, is a way to remove the duplicates. Otherwise, the speed calculation will complain. So there are duplicated values in the data set. And here we are just ordering them by time, and then we are removing the duplicates that have the least amount of empty values. And then the actual outlier removal, it's here. So we're gonna look at the speed of the buffaloes. And we see that there is a long tail because there are some very high speeds over there. Yeah.
Sorry.
So I remember Anna was saying that we should know which NAs we want to remove. So how exactly do we know which ones we want to remove?
I mean,
So often you don't know. It's just you have these duplicated timestamps. You have no idea why. But this piece of code retains the one location from all the duplicates that contains most information on the other attributes, and that's kind of handy. So as you have to make a random choice, you make this one. But you could make...
Yeah, but these are duplicated in time and location. So it doesn't matter really, especially for the purpose of this code in which we are calculating speed. If the timestamp is the same and the location is the same, the speed is the same.
Yeah, so this one actually just checks for duplicated timestamps. Locations might be off. So it might be off for several reasons, because maybe so if it's because of the different transmissions, the number of decimals sended can be different. So then the location is not exactly the same, or because actually the GPS was going crazy for some reason with the exact same timestamp and collecting 5 different positions. I think normally it's actually nearly the same position with the same timestamp. It can happen that you have multiple positions, and how on earth will you know where the animal actually was if you have 5 different options? So you have to make a random choice. So that's one of the random choices you can make. There's no right. There's not the absolute right way to do it. You have to make one that you can live with and say like, yeah, I think this is good. So that is the best option.
But these are the locations that contain the most amount of data. So the most complete ones that also have the, I don't know, if you don't work with terrestrial animal, but with flying things, then with height, that usually is not transmitted in some of the duplicates, and all the other information. And sometimes you see that the duplicate is exactly the same, but then all this information are empty for one of them, and the other one is very complete, and so you keep the most complete one. So here we looked at the speed, and then we are gonna look at the last quantiles of the speed. So you get printed there that most of the speeds go up to 0.8 meter per second, and then you have here larger speed. And if we plot this, also you see that here there is this big jump. So these are plotting the quantiles, and you see that there is a big jump between 0 point something less than 1 meter per second and then 17.
So I have a question. Like, if you consider only these points, these outliers based on speed, I'm wondering when we are studying interaction between prey and predator, we may have like huge gap because they were running from prey, attaining some speed that they couldn't have attained like in normal time. So you have this gap, but many points on this side, and if you decide to cut it, you have got another biological relevant fact that just the mathematics has called them outlier, but really something happened over there. So how do we account for that in cleaning
usually,
the data?
I mean, this is just an example, but usually you're going to remove speeds that are really outside what is realistically feasible for that animal. Then, of course, you can find exception, like we had the TIG studying bats, and then they found that actually bats fly at much higher speed that we would consider. So this is just an example. Of course, we should be careful. It's not that we are going to always remove the last quantile, so you still look at the data and see what is possible. But earlier, the example with the bats, there were bats flying at 100 meter per second, and this is really not realistic. So, don't know.
And I
Or
think in the
any
case
other.
of a predator-prey interaction, you would see those high speeds repeat more often
yeah,
than just
over
one
time
as an
also.
outlier.
Just because if it is separated from a great distance of time lag between them, you might consider, this, they can be separated repeated as many times, but a low frequency.
Yeah.
But with many frequencies that they are being chased.
Yeah. Yeah, the judgment is really based on the study system, so your knowledge of your study system.
In the Paul Cross's buffalo data, there's one outlier that's clearly a behavioral outlier, not a location error, because the buffalo goes from one side of the home range where it was to the other and stays there, and it's not heavily repeated. Like in all the buffaloes, you only see that once. You see some other cases where you can't tell if it was behavior or GPS error.
But then it still stayed on that side.
Yes.
It's not just a one-time thing.
Yes.
So it's not like this outlier
Yeah.
that was out there. So
Yes.
that's why you always explore your data. You're not just going to blindly apply a speed threshold on the entire data set. You first look at it. And as Chris was saying, I mean, this can happen for some behavioral thing, but then the animal is not going to teleport there and then back. So usually if it goes there, then it stays there for some time. So if you look that, I mean, if you see that there are these instances in which the animal appears somewhere else and then disappears, then most likely, unless it's the last point of your trajectory, and otherwise there is. And it can be informative. Sometimes it's not even that it's a problem of the GPS, but sometimes you are including data of before deployment, for instance, and then there is someone with the car driving and with the tag on it, or a poacher or whatever, and then you have this tag in the car moving. Or once we had a bird that was moving, I think it was a vulture, flying very fast in the middle of the sea, and then we realized it was on a boat going. So, I mean, you always try to first understand what's happening. And here, these are just the tools, but then, yeah, please, with care. So it's always good to think before removing data, for sure.
And it also depends a bit on the question. So sometimes you have to think about what you're losing. So if you say like, so I remove some true high speeds, but for my question, that is actually not really relevant.
Also,
Before spending days and weeks trying to find out which one is true or not, think about the trades-off. Like, do you really need that one location that had the right high speed, even if it's true, or dropping it, it's okay for your question. So it's also because depending on the amount of data that you have, but if you have 700 individuals and you have to like go through all of them, because maybe one of them actually you capture one of these high speed moments, or two of them, it's lots of time investment. So always think about how much time am I investing in actually looking for anecdotes? Is it relevant for my question? It's just, if it's relevant for your question, go for it. But if it's not relevant, it's okay to lose those 3 points because you have another 10 million that are useful for what you're analyzing.
Yeah, I agree. And to add on that, like this expectation that you get the data set, you clean the data set so you have it ready for all the analysis of the next years, this isn't gonna happen. Usually you have your data set, you clean it for your purpose, and then if you have to do something else, you will have to clean it again and take a different portion of your data and so on. So this subsetting and data massaging, you'll have to do several times for all the questions. So it's not gonna be this one-time cleaning that then lasts forever, unfortunately. Yeah, so definitely depends on the purpose of your question. Yes, so just to quickly conclude this example. So again, this 15 meter per second is very arbitrary, but in this example, we are using just this threshold. And then we can use a while loop in which then you can replace the speed that you think is more appropriate for your animal. And we are just gonna recalculate the speed iteratively until there is no more speeds that are equal or bigger than 15 meter per second.
So if I just can add, so the reasoning behind this is that sometimes, so GPS can do crazy stuff. So they can jump really far away, and then you have like 3-4 locations there that are not real, and then it goes back to where it actually is. So if you only remove once the speed, you still have the 5 locations there that are not true, and you still have high speeds. So that's why we do the while loop in these cases, that there are like these several positions that are not true to make sure to remove them all. Because we have encountered this, so we decided, okay, let's just do always the while loop, and then we are sure we remove those high speeds.
Yeah, and we just save it again for next days. So this one is cleaned. So we have 10 minutes left, but most of these things we already mentioned, so I think we can go pretty fast, because until 6, right? Okay, we talked about missed fixes earlier, and this is basically when, again, your device is scheduled to collect data every 10 minutes. At some point, the animal goes into its den, or it's a forest animal, and there is a lot of forest coverage. The satellite doesn't get enough satellites to actually find the location, and so you have empty locations in best cases, or 0, in the worst cases, but usually empty locations. So they can be informative. So we tend to just drop them in most cases. Again, depends on the question. Sometimes I'm not interested in the empty location. I just want to calculate speed or whatever. It's going to complain if I have empty location because it says I cannot calculate speed. I don't know where the animal is. But sometimes we can use them to understand something about the animals. Because again, there are probably repeated patterns in the life of an animal or the life cycle in which we don't get locations. For instance, in the den or in the forest and so on. So we're going to use the fishers as examples. We are going to take one of them, one ID, Leroy, and we are just going to pick 1 year of data in 2009. And then to find out what the misfixes are, it's if you have empty locations, it's quite easy because you just use this st is empty. So it's a function from the SF package, and it's going to just take those observations that have empty geometry. So I isolate those, and I call them not successful fixes. And then I take all those that are the opposite, so non-empty, and I call that successful fixes. I bind them. In this case, these fishers live in the New York time zone, so I'm going to transform the time to a time zone that I can interpret for their behavior, and then I'm going to plot. So in dark color, we have non-successful fixes. In light color, successful fixes. And again, we know these fishers are nocturnal animals, and so during the day, they're probably denning. So during the day, between 9 and 4 p.m., 5 p.m., it's where we have the highest amount of missed fixes. We can imagine probably because they are denning at the time. And just as an exercise, we can do the example the same example, calculating this per date. So also this might tell us something. I mean, it's not the case of this animal, but if animal hibernate or something, so this could tell us if there are certain times of the year in which we always get misfixes compared to other times of the year. And now back to interpolation and thinning. We talked about this earlier. I'm just going to show 2 examples. You already know what is the consequence of interpolating. And here I'm also going to reproduce one of the plots we looked at earlier. We use again Leroy. And when you have missing location, so when you have empty geometry, it's very easy to interpolate because we can just feed the object to the empty interpolate, a function from move2. And this will recognize what are the time steps at which the location is missing, and based on the previous location and the following location is going to do a bilinear interpolation. So it's just going to take the distance divided by the time gap, and it's going to interpolate the points. And so we can plot this, and this is the same example I showed you in the presentation. You will see that all this big gap between consecutive successful points, there is just a line of interpolated locations. Yeah, please.
So in the function interpolate, there is any determining of the function of how often do you want the interpolation? Because I see there's some areas that because there's time longer.
Yeah, so in this case, it just takes it from your data because the sequence of timestamp is there. We did not remove them. So there is a sequence of timestamp and some of them are empty. So it's just gonna fill in those timestamps.
Okay.
But then I think tomorrow, or I don't remember when, there is also another example in which you can actually give it a sequence of timestamp at which you want the interpolated points.
So in the GG animate example, in the visualization, there it's an interpolation every hour. So it just takes every hour and interpolates. In the vignette that I then showed you, so each animation kind of has a different interpolation. So there are many ways how to interpolate. It's just why you're doing it, and for animations, it's kind of, so when I was doing the code, it was kind of the trade-off of how long it takes, how many frames you get, because if you interpolate every 10 minutes for 1 year, that is lots of positions, because it actually doesn't have a missed fix. It's just like it does all of that. So you have to kind of think about, if you're doing animations, how big the area is, how long the time period is, and then to have a nice visualization how much you interpolate. But that, yeah, so.
Yeah, and here in the help file of the function, you see it's quite flexible. You have here your move2 objects and here a time argument. And here it says that time is the times to interpolate to if missing the interpolation is to the empty location. So you can give this time argument if you want. Gives the sequence of timestamps for which you want to interpolate locations, and if not, it just does it for the empty ones.
Sorry, it's not. I don't know if it's possible to interpolate taking in consideration the tortuosity of the other data.
We will see that tomorrow. So
okay.
Not interpolation, because it doesn't know how tortuous is the data. Yeah. But then there are methods that we will see tomorrow that take into account the movement process. So we'll take into account how the animal moved in a certain window to then define a probability of where the animal could have been in those time gaps. Yeah, it's a bit more complex. We see that tomorrow.
So if I understood well, we can set the interpolation interval by ourselves, but otherwise if we do not do that, the function automatically fills this interpolation GPs fixes based on the previous and the next immediate GPS location.
Mm-hmm. It's always done based on the previous and
okay, so on each case, I think it's better to do by default method, because otherwise it will measure based on the sampling intervals of these locations, because otherwise you are entering the same interval for each location. But maybe they are not the same interval.
Oh, but it's the same. You're still inventing data.
Yeah. That's in essence that's that. But
yeah. Don't think too much about this, because we don't recommend it. We need to show it, because again, for visualization or other purposes,
Yeah.
you might need to do it, and you can do it even too easily, I would say. but
Yeah.
but don't do it if you don't
Okay,
really
okay.
need to. You're still, it doesn't matter. So if you have a gap, because your device is supposed to record every 10 minutes, and then your animal is in the den, it means you have a gap of 2 hours. In those 10 minutes, in that case, it's quite safe because you know the animal has been in the den, so it's no harm done. But if you have a gap because the animal was in the forest and it moved a lot, you are still assuming with the interpolated location that the animal moved in a straight line in the past 3 hours. And this is probably not the case.
Yeah. Okay. Thank
So
you.
whichever way you do it, still that information you don't have. So if you create it, you are making it up.
Maybe there are, in these cases, as far as I read, it's the best working method is the state space models, which work well in these cases to reconstruct the segments and tracks. I don't know if you have worked with this kind of methods.
This specific, I don't know.
Yeah, yeah, it's most of the same, but are more accurate. It's just a matter of accuracy.
Yeah.
Yeah. Okay.
So
Thank you.
CTMM has a nice path reconstruction, and otherwise tomorrow we look at dynamic Brownian bridge, and that also gives you, but it doesn't give you an exact location. It gives you a probability of, based on of how the animal is moving, the probability of where it could have been in that gap, which is more realistic, basically. Yeah. But we see that tomorrow.
The ST is empty function, does it read 0, coordinates as a location or as an
No,
empty?
so the ST is empty is a function that basically gets the empty locations. So all those locations that have NA,
Okay.
so it doesn't work with 0, 0. You would have to transform the 0, 0 to NA
and then
use ST
okay,
is
okay.
empty, which is no harm if you know your animal lives very far away from the center of the 0, 0 for whatever coordinate system you're using. But if your animal moves in that area, then it's very tricky because you never know which one is the right location. Yeah? Okay. Where we? I was showing this plot. Yeah, but we saw this already in the presentation, so it's nothing new. Again, when we interpolate these points, we are including autocorrelations because since we don't know what the animal actually did in that time, the animal could have turned, meaning breaking the correlation structure in its movement. But since we don't know what the animal did, we are assuming it's moving straight, which means the direction at step 2, I artificially assume that it's very correlated to the direction at step 1. Same thing with the speed. Yeah, so here in this case, we are looking at autocorrelation in speed. So of course, if I take the time gap, if I take the distance in that gap and I divide it by the time, I'm just breaking the speed in all equal parts. So I'm artificially assuming that the speed is going to be constant for that whole time, which we don't know, probably is not the case. But so just adding reasons why not to interpolate, basically. Yeah, and here just a brief example before we are done about what happens with thinning or subsampling. We are using, in this case, simulated trajectory. We are simulating a correlated random walk of 1,000 steps. And then, with the 0.99, I think this is the correlation in azimuth. And then we are just thinning it by taking one location every third location. So we are taking the simulated track, r.track, and then there we are taking a sequence that goes from 1 to the length of the locations, taking 1 every 3. So it's just an example to see what happens when we remove some locations. And then we are going to compare the distribution of speed. So we're going to calculate speed on the original simulated track and on the thinned track. And we see that the distribution is different. So how is it different? We're going to plot this. And this I already showed anyways in the presentation. So in the lighter color, all the positions, so the entire simulated trajectory. And then in gray, so in what you see here in the back, the every third location. And so what happens is that the average stays more or less the same, but then, so the mean is more or less the same, but then the overall distribution changes. And so only when we have all the location, we have actually this wider range of possible speeds. And so the more we subsample, the more we reduce the variability in speed. And this is just showing again the same. So it's quite different, but then the distribution overall is different, but then the mean, it's quite similar. And this is also kind of the conclusion I made at the end of the presentation. What are the final notes on thinning? Sometimes it's useful if we want to compare groups, we need to be aware of what is the consequence of thinning. Of course, we are underestimating speed. We are also underestimating the variance in turning angle and tortuosity. But it could be useful in some cases. Definitely more useful than the interpolating. In this case, we are not making out data. We are leaving out data, which can be a problem, but at least it's still realistic if we are aware of the consequences. And I think that's it for today, right? Yes, please.
Sorry to bother you.
No, please.
I have a question regarding this last part, because there are two, at least the two methods with which I'm most familiar with. It's resampling and subsampling, and both of them have their own drawbacks. And which one do you recommend more in each case?
Resampling?
Yeah, because resampling is we are just taking data because we have at the same sampling interval, and subsampling we are taking data for each interval.
I think that's the same as interpolating.
So
resampling is kind of interpolating, I would say.
No, but resampling at least not in the sense that for example, in the MET package is explained. So because they made some differentiation. Yeah, it's a terminology thing.
It's not resampling. It's not. So when we think of
sorry.
No, I think what Martina was thinking, like you have the trajectory, and then you say every 10 minutes, and you just take it along the line.
Oh, yeah.
But AMT doesn't do that.
No.
Yeah, that's the. I think the function is a bit. The name of the function is a bit unfortunate, because it's not resampling. You're taking true data, so you're not actually making data up. Because resampling seems like, I don't know.
Yeah. Just every 10 minutes or something, or every 15 minutes.
Yeah, no. AMT is doing a very good job, and it's actually, I think from my experience, is the best thinning tool. So it's still doing a subsampling, but it's just more accurate in the way it does it, and it makes sure that if you need a regular output as time lag, so you really need data every 10 minutes, it's gonna cut it to the 10 minutes. So I think it does a very good job. Yeah. And I don't remember exactly what it does internally, but it's a bit different than, this is like kind of this removing every third location, it's like a very rough way to do it, and AMT does a much better job.
Much more accurate,
Yeah.
Just as a in the Move to package, there's also a thinning function, and it works, but it doesn't work as good as the one in AMT. Yeah, so that one is really good. There is in the doings another function that will also work better, but for now, the way it works, it just takes one location in a time window. So if you say like every hour, so it divides the day into hours, and then it takes like the first location of the hour. So the distance between those locations, if you have really irregular data, you can have one location at 10, and the next location is at 11:30, so you have 1.5 hours between it, and then maybe the next location is at 12, so then you have half an hour. So so it depends. If you have really irregular data, the AMT does a better job at sampling. So it depends a bit.
Maybe we can write it here. Do you remember the name of the function? Track resample?
It's resample. Yeah,
resample.
In the other package, there is also another package. Maybe a bit, I don't know, confused. Sorry, it's Atlas Tools, because the author made this tells apart smoothing from thinning, and it explained it in very different way, I guess. It's a bit different because I use in my own course the smoothing with the moving windows, and but it's more confusing than this is more straightforward. Yeah.
Is it resample?